Okay, topic 19-4. In this lesson, we're going to look at function applications with cones. So these are going to be a little bit different from the cylinders that we did. So let's take a look at example 1. It says a water reservoir is in the form of an inverted right cone that is 12 feet high and has a radius of 6 feet. Water is being poured into the reservoir at a height of x. So let's sketch a picture of this problem situation. So we have an inverted right cone, which means it looks like this. The vertex is going to be, or the height is going to be perpendicular to the center of the base. And we know that the radius is 6 and the height of this cone is 12. Now, water is getting poured into the cone to a height of x. So let's say the water gets to this height. Well, we don't know what this radius is going to be, so we're going to call that r. And we know that the height, whatever height this is, we're going to call this x. So let me draw. What happens is in this cone is you end up with similar triangles. Okay, and so what we have is we have the reservoir, which is the entire cone-shaped reservoir. I don't think I'm saying that right, but you get the idea. And so it looks like this. We've got the radius of 6, and since it's a right cone, we know that's a right angle, and we've got the height of 12. And then we've got the water level, whatever height the water is at, this is going to be a similar triangle to the container. So the water is going to have a radius of r and a height of x. So B says find x when the radius of the water is 4 feet. So basically if they're similar triangles, then you can just do a proportion. The radius is 6 when the height is 12 for the container, and then the water, if we know the radius is 4, what would be the height? And of course just cross multiply or take half of that. And so we get, double that, and so we get 8. Okay, so the height, when the radius of the water is 4, then the height is going to be 8 feet. Because you can see in the original container that the height is twice as much as the radius. So the water level, no matter where it's at, will always be, the height of the water will be twice as much as the radius, because that forms similar triangles inside of the cone. Okay, now C says express the radius of the water in terms of the height x of the water. So when this says express the radius, then what you want to do is, that means you want to solve for r. Or you want to write an expression for the radius in terms of the height x of the water. So we want to have an expression that says the radius equals, and you want an expression with x in it. So look at the relationship there. If we know that the height is twice as much, right? If we know the height is twice as much as the radius always, right? Then we can write our expression as the radius equals half of the height. Okay? So that would be our expression. We know that the radius is half of the height. If it said express the height in terms of the radius, then that would be x equals 2r, because we know the height is twice as much as the radius. Okay, so the radius is always half of the height. So that would be an expression of the water in terms of the height x of the water. All right, so D says express the volume of the water in terms of x. So therefore, we want to write a function for the volume as a function of x. So let's go ahead and write down first of all the volume of a cone formula, which is 1/3 pi r squared h. Okay, 1/3 area of the base times the height. And so we want this volume to be as a function of x. Or when it says in terms of x, we want only x's in that formula instead of r's and h's. Okay, so we're going to have 1/3 pi. And what did we just find on the last part, on part C? The radius equals what? We found that the radius was half of the height, right? So we're going to put, instead of r, we're going to put 1/2 x, and we're going to square that because the radius is being squared. And then the height is x. So I'm just putting it in terms of x instead of r's and h's. So now let's simplify that. So 1/2 x squared, this is going to give me, so I've got 1/3 pi, this is going to give me 1/4 x squared when I square the radius. Okay? And then let's simplify that down even more. And let's multiply the fractions together. So 1/3 times 1/4 is 1/12. And then I've got pi, and I've got x to what power? X squared times x is going to be x cubed. And so we simplify this down as much as possible, and then here's a formula for the volume as a function of x. So if we know what x is, well, if we know what the height of the cone is, then we can just plug that in and find the volume. So let's do that then. Part E says, find the volume of the water when the height of the water is 9 feet. So here's our formula for volume that we found, dependent on the height of the water. So let's plug in 9 for x, right? Because the height is x. When the height of the water is 9 feet, 112 times pi times 9 cubed. Again, we're going to leave it inexact because it doesn't say to round. So use your calculator. And 9 cubed times 1/12, or 9 cubed divided by 12, should come out to be, and you can put it as a decimal, 60.75 feet cubed. Okay, so 60.75 pi, cubic feet or feet cubed. Okay, so see, if we just know the height of the water, we can plug it into that formula and find what the volume of the water would be. Because the radius is changing. So we didn't know the radius there, so we would need a formula based solely on the height. Okay, so let's try another example. This one says water is flowing at a rate of 5 meters cubed per second from the tip of a tank that is in the shape of an inverted right cone. The cone has a diameter of 60 meters and a height of 120 meters. So let's draw a sketch of this problem situation. So here's my inverted right cone. They don't have to be inverted, they could be the other way. And I know that the radius, the diameter is 60, so I know the radius is 30. And it's a right cone, so I know this is going to be a right angle right here. And then the height is 120. Okay? All right, so that's the size of the tank. So we've got the tank. Let's draw our similar triangles. We've got the tank that is like this. We have the radius 30 and the height 120. And then we have the water level, the shape of the water. And it's going to be changing, so whatever the radius is and the height, they're going to be in proportion to the tank. So let's find the volume of the water when the tank is full. So again, volume of a cone, right? 1/3 area of the base times the height, so 1/3 pi r squared times h. And let's go ahead and plug in. If the tank is full, then the radius is 30, and my height would be 120. Okay, so leave it exact, but work it out. punch in your calculator. The volume of that should be 36,000 pi meters cubed. Okay? Now it says, how many minutes does it take to drain the tank if it is full? So let's look at in terms of the water is flowing at a rate of 5 meters cubed per second. So the volume in meters cubed over the time in seconds, the rate it's flowing at is 5 meters per second. So if I know the volume of my tank when it's full is 36,000 pi, then how long is that going to take to drain? Okay, so cross multiply or take 36,000 pi divided by 5, and we get, for the time, 7,200 pi. Okay, so that is in seconds. So it says how many minutes. So we would want to do what? Good, we want to divide that by 60. So the approximate time in terms of minutes would be 377 minutes. Okay, so calculate that up, make sure that makes sense to you. All right, so part D says find the radius of the water in terms of the height of the water. So if we want to find the radius, then we are going to solve for R. Okay, in terms of the height. So let's look at the proportional relationship in the tank. When the radius was 30, the height was 120. So the height is 4 times as much as the radius, right? The height is 4 times as much as the radius. So that would give us the radius equals 1/4 times h. Okay, if it said it the other way around, find the height in terms of the radius, the height would be 4r. All right, so now let's plug it in. It says find the volume of the water as a function of the water level h. So we're working with cones here. So the volume of a cone is 1/3 pi r squared h. So I'm going to do it as a function of the height of the water level. So I've got 1/3 pi times, we just found that the radius is 1/4 of the height, and then times, squared, don't forget squared, and then times the height. Okay, so let's simplify that down. So we've got 1/3 pi. When we square the parentheses, we get 1/16 h squared times the height. And then our final equation simplified all the way down would be 1/3 times 1/16 is going to be 1/48 times pi times h cubed. Okay, so if we wanted to find the volume of the water when the height was, say 20 meters, then you could plug in 20 for h and then work out that equation and find the volume of the water. Okay, so that is function applications with cones.